A massive gantry machine stands ready, its structure designed for both scale and versatility. The PMG 6000 demonstrates not only milling capability, but also turning and grinding within the same setup. Its size alone gives an impression of industrial strength that demands respect. The foundation lies in its spindle, 43 kilowatts of power, 900 newton meters of torque, and a direct drive reaching 6,000 revolutions per minute. Paired with a universal head adjustable in 2.5 degrees increments, it ensures flexibility across a wide range of tasks. Longitudinal travel extends to 6,000 millimeters, vertical travel reaches 400 millimeters, while cross-travel covers 500 millimeters. The table-to-ram distance of 2 meters allows work on large components. These numbers show how scale and accuracy merge in a single platform. The machine integrates advanced cycles, vibration suppression technology, and an automatic changer for 80 tools. In action, a U160mm with 8 teeth removes 774 cc per minute at 1.075 mm per minute feed. A high-feed 0100mm pushes removal up to 960 cc per minute. Observing these rates, one realizes how material seems to vanish in seconds. Drilling at E70 operates at 910 revolutions per minute, while a helical end mill E80 removes 459 cc per minute with 60% power load. Such balance between efficiency and energy use is impressive. Custom heads, pendulum machining, and palletized setups add to its adaptability. It becomes clear this platform is engineered to cover countless manufacturing needs. Inside the Shanghai workshop, activity flows with purpose. Equipment arriving for repair is dismantled, thoroughly cleaned, and inspected step by step. Technicians then create a repair plan, including replacement parts and upgrades. Dynamic balancing follows, ensuring stable operation. Final assembly completes the process under strict German standards. Each stage feels like restoring strength to valuable machines. With this structured workflow, long-term reliability and safe operation become assured outcomes for industries worldwide. A stream of fire and molten energy defines the beginning of steel casting. Inside the foundry, the process connects centuries-old knowledge with modern engineering. Each sequence reveals not just technical skill but the shaping of one of industry's strongest materials. It is striking how raw heat becomes controlled progress in this space. The journey begins with pattern making. Wooden or resin models are constructed to represent the final casting's shape. These patterns guide the creation of sand molds and allow accurate replication of design. Even the smallest features must be captured at this stage, as they later influence the strength of the part. The care invested here sets the tone for the entire process. Molding follows as specialized sand is packed around the pattern. Binders are added to create a stable structure capable of holding molten steel. Afterward, the pattern is withdrawn, leaving a cavity identical to the intended shape. There is always a sense of suspense when the mold is opened, revealing the space where steel will eventually flow. Next comes melting. High-capacity furnaces transform solid metal into liquid steel at temperatures exceeding 1600 degrees Celsius. Alloying elements are introduced to achieve required mechanical properties. The glow of the furnace makes the atmosphere intense, as if raw energy is being forged into durability. Pouring then takes place. Molten steel is guided carefully into the prepared molds. Speed and flow must be balanced to avoid defects or trapped air. In this moment, timing and control decide the success of the casting. The molds are then left for cooling, allowing the steel to solidify with its intended shape. After cooling, shakeout begins. The sand mold is broken apart to reveal the rough casting inside. Excess sand is removed, and runners or risers are separated. It feels almost like uncovering strength hidden beneath layers of earth. Heat treatment follows, where the casting is reheated and cooled under controlled conditions. This step enhances hardness, toughness, and resistance. Machining comes next, with cutting tools refining dimensions, drilling holes, and shaping surfaces. Watching a massive casting being refined into precise geometry shows the harmony of raw power and control. The process concludes with inspection. Castings are examined using visual checks, dimensional measurements, and sometimes ultrasonic or radiographic testing. Only when standards are achieved can the product move forward. Each inspection carries the weight of responsibility, ensuring safety for structures that will rely on this steel. The energy of industrial forging is on display through the operation of Otani's air stamp hammers, machines designed to deliver consistent force in shaping metal components. These hammers are engineered to handle large production volumes while maintaining high reliability. It feels powerful to see raw energy controlled with such technical structure. The process begins with compressed air directed into the upper piston chamber. This pressure generates the force required to move the ram downward. By regulating air supply, operators can control both the speed and the impact strength, allowing the hammer to adapt to different forging tasks. The responsiveness of the ram makes each strike look both forceful and controlled. Next comes the split-type ram guide design. This feature allows the ram to be dismantled vertically from either side, providing easier maintenance and reducing downtime. The system is built to withstand repeated heavy impacts while ensuring long-term alignment. One cannot ignore how practical this design becomes when considering factory efficiency. Safety is a critical part of the sequence. A ram safety catch lock is integrated, preventing the ram from dropping if power failure or unexpected interruption occurs. This safeguard not only protects the equipment, but also shields operators from risk. It is reassuring to see how mechanical safeguards are built directly into production machines. The hammer then demonstrates striking force. Models such as the Dymax 45E and Newton 30,000E produce immense energy, suitable for forging a wide variety of parts. By combining compressed air control with structural durability, these hammers adapt to both small and large-scale production. Each blow feels like a rhythm of industry shaping the future. Throughout operation, efficiency is central. The ability to produce large quantities of components with stable quality makes these machines essential in forging lines. Reduced maintenance, downtime, and adjustable energy delivery further enhance performance. The harmony between power and adaptability is what defines these machines. Finally, the overall design reflects decades of forging expertise. Every detail, from piston control to guide construction, serves the demand for consistent output. It leaves an impression that forging technology, though forceful, can still show remarkable refinement. A row of machines waits in sequence, each one contributing to the making of a tubular motor stator. The setup is semi-automatic, balancing human oversight with mechanical consistency. The process starts with slot paper insertion. Sheets are placed into the stator slots to provide insulation, ensuring that the copper windings will not short against the steel core. Even at this early stage, the precision of placement matters greatly to the stability of the motor. Next comes coil winding. Copper wire is wound to exact specifications, building the electrical pathways required for performance. The steady rhythm of the wire winding creates a striking visual of technology at work. The wound coils are then transferred to the inserting machine. With controlled force, they are pressed into the stator slots. Every motion feels purposeful, showing how accuracy is achieved through both machinery and timing. After insertion, a lacing machine secures the coils, binding them firmly in place to withstand mechanical stress during motor operation. The stitching motion of the lacing adds both strength and durability. Finally, the forming machine shapes the entire stator assembly. The finished component reflects an impressive combination of engineering and design. The making of a forged ring starts with a heated steel billet, glowing intensely as it emerges from the furnace. That first burst of color instantly conveys the sheer energy stored within the material. It is almost hypnotic to watch raw metal radiate such strength before shaping even begins. The billet is transferred to a powerful press, where immense force flattens it into a disc. The controlled compression ensures uniform density, critical for the integrity of the final product. Each thunderous strike echoes with the determination behind industrial forging. Next comes piercing, where the center of the disc is opened to create a hollow shape. The piercing tool drives through the hot steel, forming the initial hole that will later define the ring. At this stage, the transformation feels bold, as the steel resists but yields under relentless force. The hollow blank then moves to the ring rolling mill. As the rollers rotate, the ring expands in diameter while its wall thickness becomes more refined. The sight of the ring growing larger with every pass carries a sense of unstoppable momentum. This rolling process achieves not only the required dimensions but also enhances the mechanical properties of the steel. After rolling, adjustments are made for roundness and uniformity. The glowing ring continues to turn until the desired measurements are reached. Watching the circle take on its near-final form sparks an appreciation for the balance of power and accuracy. Finally, the forged ring is left to cool under controlled conditions. Strength, durability, and geometry are now locked into the steel. What began as a simple billet has now become a robust ring, ready for demanding applications. Power generation begins with solid foundations, and every component in this workshop plays its role. Steel frames are cut, welded, and shaped with accuracy before becoming parts of a generator. Laminated stators are produced and coils are wound in-house, ensuring durability. Rotor windings are created with robust machines and undergo drying and balancing to minimize vibration. The final assembly integrates all units, followed by strict functional tests that verify performance before packaging for shipment. A hot crimping machine shapes the connection of cable terminals without the need to strip insulation. The process looks both powerful and efficient. The cycle begins as the terminal is positioned in the welding head. Heat and pressure combine to form a solid joint. You can sense the strength behind each operation. Advanced parametrization allows separate setup for the first and second weld sequences, including holding and dwell times. Such flexibility ensures consistency in demanding applications. Optional features add versatility: a 90-degree swivel welding head, a height-adjustable rotating desk, and a tracking system for welding parameters. Each detail reinforces technical reliability. The production of a PDC drill bit begins in a workshop where raw materials and technology intersect. These drill bits are vital tools in oil and gas exploration, designed to cut through rock with strength and consistency. Each stage in the process shows how engineering skill transforms basic components into something with immense power underground. The first stage involves preparing the steel body. Solid steel bars are cut and shaped into cylindrical forms that will serve as the backbone of the drill bit. Welding equipment and lathes are used to refine the structure, ensuring that dimensions meet strict specifications. It is fascinating to see how solid metal is gradually guided into the required form, as though the material is submitting to both heat and mechanical force. The glowing sparks during welding add intensity to the scene, reminding us of the strength being built. Once the body is prepared, the focus shifts to creating blades. Alignment is critical here, since even small errors would affect the stability and efficiency of drilling operations. At this stage, the drill bit begins to resemble the powerful cutting tool it is meant to be. There is a moment of anticipation as the structure finally looks like a tool ready for its role. The process then moves to finishing and balancing. Surfaces are ground, cleaned, and coated to protect against corrosion and wear. A balancing machine ensures that the bit rotates smoothly under extreme conditions. This part of the process highlights the remarkable mix of physics and craftsmanship behind drilling technology. Finally, the drill bit undergoes quality control. Inspectors check welds, alignment, and cutter placement, verifying that the finished product meets performance standards. A coil of insulated cable arrives at the stripping machine, designed to handle diameters up to 50 millimeters. The feed rollers grip the cable and push it toward the rotating blades. Insulation is sliced open and separated, exposing bright copper inside. The stripped copper falls neatly aside, ready for recycling and further processing. It feels surprisingly efficient. Leaf springs for rail vehicles undergo a demanding production journey that ensures strength, safety, and durability. At the Langen & Sömmermann plant in Lunen, parabolic and coil springs are prepared for service under extreme loads. After initial heat treatment, the springs require cleaning. Grinding removes slag and scale, and then the roller conveyor system carries the parts through the blasting chamber. It is impressive to watch the process flow as loading and unloading happen at the same station, streamlining movement. In the blasting chamber, the springs are pre-tensioned with press force up to 20 tons and an upstroke of 200 millimeters. As they advance, turbines accelerate blast media onto the tension side and edges. Feed rates vary between 3 and 10 meters per minute, balancing coverage with efficiency. Strong protective curtains prevent material loss, while a noise booth keeps the environment workable. The blast media itself is carefully recycled. Shot is collected, lifted to a cleaning station, and separated from dust by air classification. Filters keep residual particles extremely low, even allowing air to be returned into the hull, saving energy. A second unit handles coil springs of varying sizes, transporting up to 60 pieces per hour. Parallel conveyors and rotating shafts guarantee even peening around every surface. By the end, the springs are clean, hardened, and immediately ready for powder coating. Watching this, one cannot help but admire the mix of force and engineering logic shaping every detail. Massive gears are born here through techniques shaped by both power and skill. Bruck GmbH employs 4-gear milling machines to handle demanding requirements. In peripheral milling, the gear blank rotates continuously as a spiral-shaped cutter forms teeth, achieving quality grade 9 for heavy-duty use. These wheels may reach 7 meters in diameter, with teeth up to 90 millimeters. Profile milling works differently. Each pitch is indexed and milled, even angled up to plus or minus 30 degrees, producing reliable gears for wind turbines. The scale of this gear case commands attention, its bulk setting the stage for demanding machining. Namco Machine and Gearworks Limited undertakes the task with determination. The case is mounted securely, and powerful mills trim surfaces to exact alignment. Line boring follows, guiding tools steadily through the housing to ensure perfect shaft passage. The rhythm of the cutting tool feels intense, almost alive. Each pass deepens the accuracy, and soon the structure is ready to endure heavy industrial loads. At first glance, a thick steel plate looks unremarkable, yet it holds the potential to become a powerful screw flight. The process begins by selecting a plate measuring 48 inches in diameter, 48 inches in pitch, and 1¼ inches in thickness. This size demands robust forming equipment, and the true helix system is designed for such work. Once in place, the plate is engaged by hydraulic forming tools that gradually apply force. The machine bends the steel smoothly, turning a flat section into the start of a helix. Advanced software and PLC controls guide the movement, ensuring consistency across each piece. The transition from flat to spiral feels almost effortless with the technology involved. As the forming continues, the helix grows with exact spacing and alignment. Each section maintains uniformity, avoiding distortion even under immense pressure. The result is a screw flight that matches the intended dimensions with remarkable accuracy. By the end, the flight is released and attached to a shaft tube. Workers use measuring tools like a ruler to confirm that the alignment and size are correct.